Hello everyone. Today I'm going to talk about noise in a 5G communication channel. You know that we use cam modulation in 5G and ideally we would like to use higher order constellation. Ideally we would like to use 4 QAM, 16 QAM quadrature amplitude modulation. You're familiar with this. 32, 64, 256 and 1024. So ideally we would like to work with this QAM 1024. Now why would we like to work with higher order constellation is because bitrate is equal to M times RS, where RS is the bandwidth, where RS is the symbol rate. Typically it is bandwidth for 5G, and M is cardinality of the log 2 cardinality of the constellation. So we can increase the bit rate by increasing M. For 4 QAM, M is log 2 4, which is 2. For 16, it is log 2 16, which is 4. Then it's 32 is not there. Then for 64, it is log 2 64, which is 6. Then 8 and then 10. So we would like to work with 1024 QAM constellation, for which M is equal to 10. Now for 5G band is 80 megahertz or 100 megahertz. These are the typical values of band for 5G. So if we plug this in the formula, RB is equal to MRS, we can achieve 10 times 80, or let's use the higher version, 10 times 100, which is 1 gigabit per second. Okay, this is 10.3 which is 9. It's 1 gigabit per second. Okay, so with higher constellation we can achieve higher bit rates, but what is the cost? What is the cost? What is the price to pay? From a bit loading formula, we have RB is less or equal to B log 2 1 plus 1 by gamma S P Rx by Pn. This is the bit loading formula, which RB is the bit rate, B is the band, gamma S is the suboptimality factor, which is deviation from the ideal constellation. I will not discuss it in detail in this lecture. PRX is the received signal power and PN is the noise power. If we do bit of a substitution, RB is MRS, RS is B, so we come to M is B log 2 1 plus 1 by gamma S PS by Pn. So in order to use a constellation with M equal to 10, there is a point that how much signal to noise ratio we need, how much SNR we need at the receiver, what should be the SNR, so that we can work with 10 QM constellation. We can work with 1024 QM constellation. If we rewrite this, M is less or equal to log 2 1 plus gamma 1 by gamma S PRX by Pn. What is the minimum SNR required to work with a 1024 constellation? Let's say, for the sake of simplicity, gamma S is 10. Now, for M to be 10, 1 by 1 plus gamma S PRX by Pn log 2 of this quantity should be equal to how much? It should be equal to 1024. In other words, 1 plus 1 by gamma S should be equal to 1024. So that log 2 of this quantity will be equal to 10. So 1 by 1 gamma S PRX by Pn should be equal to 1023. Since gamma s is 10, Prx by Pn, which is also known as SNR, will be equal to 10230. So in order to work with QM constellation, 1024 QM constellation, so that m can be equal to 10, the bit rate can be of the order of 1 gigabit per second, we need a signal to noise ratio of 10230. Now, at the moment, you may not know that whether this signal to noise ratio is achievable in practice, whether it is very high or whether it is low. At the moment, you may not know. But throughout this, but at the end of the video, you will get to know about if it is achievable or not. Let's say for 4QM, what is the minimum signal to noise ratio required? So m is 2, 2 is less or equal to log 2, 1 plus 1 by gamma s, p rx by pn. So this has to be equal to 4, so this has to be equal to 3, so it is prx by pn should be equal to 30. So signal to noise ratio at the receiver should be equal to 30 in order to work with 4QM constellation. Now, these values of SNR 30 or 10230 when m is equal to 10, are they achievable? Can this be realized in practice? For this, we need to model noise. We need to look at what is the typical value of noise in a communication channel. How much is the contribution of the noise in the communication channel? Typically, noise is assumed to be white Gaussian in a communication channel. The major impairment is the thermal noise, which is due to random motion of electrons in a conductor, because of which we have non-zero voltages. Now, in order to model this thermal noise, we need to look at the following equation. From the Johnson-Nyquist equation, which models the power spectral density of thermal noise, the power spectral density of thermal noise can be expressed as hf over 2 divided by e raised power hf by kt minus 1, where k is Boltzmann's constant, h is the Planck's constant, f is the frequency, and t is temperature in Kelvin. If we suppose that f is greater than, if f is much larger, if it is very large, we can approximate e raised power x as 1 plus x square by 2 factorial. So, e raised power hf by kt will become 1 plus hf by kt. And 1 plus hf by kt, 1 plus hf by kt 1 plus hf by kt minus 1. So 1 and 1 will go. In the denominator, we will have hf by kt. So if we simplify this equation, the power spectral density of noise will be kt over 2. It will be kt over 2. Power spectral density of noise will be kt over 2. So what we have from this equation, what is the major conclusion of this equation, is that the power spectral density of noise is independent of the frequency. There is no frequency term involved in the expression of power spectral density of noise. Sometimes this kt is written as n0. So you may find in some textbooks that it is also written as power spectral density of noise is n0 by 2. However, the major idea is that the noise is independent of the frequency. However, keep in mind that this equation is only valid for low frequencies. If f is greater than, if f is much larger, close to infinity, the power spectral density of noise becomes 0. So we need to take care of the frequency range we are interested in. Now, from the above expression, we saw that the power spectral density of noise is flat up to certain frequency, which is known as threshold, and after the threshold, it decays exponentially to 0. And this threshold is around 10 raised power 12 hertz. In other words, 1000 gigahertz. Okay. But our systems, our communication systems, let's say 5G, they work around 3.6 gigahertz. And in future, they will work around 5G will work around 26 gigahertz. So we are very far from this threshold. So we can approximate that power spectral density of noise for our communication channel is flat. is flat. Now, how can we estimate the power of the noise? We can estimate How can we estimate the power of noise within our band, within our frequency range? As we saw earlier, it is important to know that SNR was required to be 30 or 10230 for 4 qm and 10 qm constellation respectively. In order to see that whether this is practically achievable, we need to calculate the noise power. How can we calculate the noise power? We know that the 5G has band width of around 80 megahertz or around 100 megahertz. So what we have to do is basically integrate the power spectral density over the frequency ranges, over our frequency band. So we integrate the power spectral density over our frequency range. We will get KT. So this will be twice, because it's symmetric, KTB, KT delta F, and DF. So it will be simply KT over 2. So it will be simply KTB. So noise power can be written as KTB. So what are the typical values of the noise power in 5G communication channel? The Boltzmann constant is 1.38 into 10 raised power minus 23. Temperature is around 300 Kelvin, and the band is 100 megahertz. So this comes down to power of 4 into 10 raised power minus 13 watts. So this is very low power as far as our communication channel is considered. Power is not a major impairment for 5G communication channel. You can see the value is very low. Even if we want to achieve SNR of 30 or even 10230, it is possible because the noise power is pretty low. So we can work with higher order constellations. The noise is not a major impact for a 5G communication channel. Instead, what the major impact is, attenuation and intersymbol interference are major hurdles that we need to take care in a 5G communication channel. And as far as noise is concerned, we can manage that efficiently.